right, welcome to part 2 of the adaptive control section. So in the last video I showed a control block diagram. I'm going to just redraw it just to make sure everybody's still on the same page. So I've got a reference signal that goes through some transfer function to give me a model trajectory. And the reason why we have this, by the way, is like, let's say R is a step input and your system has a lot of mass. A step change command is going to be a very harsh transition. It's going to cause accelerometers to kind of go crazy, and it's going to cause a lot of noise in your sensors. And so a lot of times it's nice to sort of like bring that up slowly. And so the easiest thing to make F here is just a simple second order transfer function. And you'll see I made the gain the final value equal to 1, so that the final value of xm is equal to r. And so if you do the inverse Laplace and cross multiply, you end up getting that mx double dot plus 2 lambda 1 x model dot plus lambda 2 x model equals lambda 2 r. And those are sort of your model dynamics. So this is running, you know, on the computer. Okay, so then this is going to have an error signal, which your book, well, I say your book, I'm using the book, I'm using Applied Nonlinear Control by Slotin. And so in the book they use x tilde here, and so this is your error signal that's going to go to your controller, which is going to create your control input, which is going to go to your plant, it's going to create your output. I'm assuming unity feedback here just to make the math a little bit simpler. And the idea is how do you make C to stabilize the system? So this is kind of independent of your controller. This is just like a model reference dynamics. It's not really part of your controller. What we need to do to stabilize the system is first we need to look at our dynamics. So our dynamics here are mx double dot equals u. Okay, those are our dynamics. That's pretty simple. It's second order. It's got 2 poles at the origin, right? So if I did big X over big U, I would get 1 over ms squared, right? And so I've got 2 poles at the origin, which means I'm marginally stable. So I need to have a control system to stabilize the system. I don't need to worry about steady state error for a step change because I've got 2 poles at the origin. Actually, I don't even need to worry about steady state error for a ramp change because of 2 poles at the origin. What I do need though is I need stable tracking dynamics, and so since I don't need interval control, I can really just use PD control. Now, because M is hitting this left half side of the equation, instead of just using a PD controller just like willy-nilly, I'm going to say that U is M times nu, and nu I'm going to make x model double dot minus 2 lambda x model dot minus lambda squared. Sorry, this is going to be x tilde, and this is going to be x, this is x tilde dot. So this is your derivative gain, and this is your proportional gain. And I use 2 lambda and lambda squared here to critically damp the system, so my closed loop dynamics are going to be critically damped. Now the thing is you can always tune your reference dynamics, so if you have a step change, you can always make it oscillate just with the model reference dynamics here, and your closed loop, your tracking, this is really your tracking performance. Your tracking performance would be critically damped, okay? Now, if you made your tracking performance not critically damped, if you made it oscillate and you made your reference dynamics oscillate, you would have a lot of oscillations there, and that wouldn't be a good idea. So the better thing to do is to tune your model reference dynamics and then tune your tracking performance separately. Just tune those 2 things separately. Okay, these are the same variable here. If I plug this into here, and then plug this up here, what I'm going to get is I'm going to get mx double dot equals x model double dot minus 2 lambda x tilde dot minus lambda squared x tilde. And if I bring this to the other side, there's an m somewhere. So there's a, I'm going to put an m here. Okay. And so if I bring this to the, actually the m's just cancel, I forgot. Anyway, so if I bring this to the other side, I'm going to get x tilde double dot, because that's x minus, oh, I forgot to tell you what x tilde was. X tilde, right, is x model minus x. Wait a second. Oh, man. Hang on. real quick. Is that x minus x model? What? No. Oh, okay. This isn't a big deal. Okay, the reason why this isn't a big deal is because, so the book says it's this, okay? Which means, okay, this is kind of a hack here. This is E, I'm going to multiply by -1, and this is going to be x tilde, okay? So everything's fine, all right? I just need to make an update of that. So my error signal is x model, so I'm going to make E equal to x model minus x, right? And then I'm going to make x tilde equal to -E, in which case x tilde is x minus x model, and everything shakes out. Now, why do you have this -1 here? I have this -1 to make sure that my control block diagram here, which I made up, is the same as the notation in the book, okay? It doesn't make a difference because as long as you make lambda stable such that this all works out, everything's all well and good, okay? I'm going to show you in the closed loop dynamics that it really doesn't matter. Okay, so I've got x tilde here, x tilde here. I bring this to the other side. I'm going to get x minus x model. X minus x model is x tilde, so I get x tilde double dot plus 2 lambda x tilde dot plus lambda squared x tilde equals 0. Okay? These are my closed loop dynamics. Okay? What's interesting about this closed loop dynamics is that because they're critically damped, I can actually bring this into the Laplace domain and give me x tilde s squared plus 2 lambda plus lambda squared equals 0. And this is really x tilde s plus lambda squared, right? That's a critically damped system equals 0. And so what I'm going to do is I'm going to let s equal, oh sorry, I need to use p, and p. So p is my Laplace variable. I'm going to let capital S equal x tilde p plus lambda. And if I take this and substitute it in here, what I get is that s p plus lambda equals 0. And then if I convert these both back to the time domain, what I get is that x tilde dot plus lambda x tilde equals s, okay? And then this, if I convert this to Laplace domain, I get s dot plus lambda s equals 0, okay? And so what I have here, this is kind of weird, but what I have here is I have two first order transfer functions. So in this case, I have a first order transfer function with no forcing function. So that means as long as lambda is greater than 0, s is going to go to 0, okay? If lambda is greater than 0, it means I have a pole in the left half plane, and so s is going to go to 0. If s goes to 0, it means that this forcing function is going to drop to 0, which means, again, as long as lambda is greater than 0, x tilde is going to go to 0. Now, x tilde, remember, is x minus x model, which means that x goes to 0, x tilde goes to 0, it means that x is going to go to x model, which means I have good tracking performance, okay? Now, this, unfortunately, is all predicated on m being known, okay? If you design your system to be robust, or if your m did not change by very much, then you'd be okay. If you didn't know what m was at all, like not even in the ballpark, then you would need to throw an adaptive controller on there to update mass. So we need to create a controller where mass updates on the fly so that we can estimate that parameter, okay? And how do we do that, okay? So what we're going to do here, so I've already, for the folks that are enrolled in this course, I've already taken notes in my Rocketbook and uploaded it to the Google Drive, so I'm actually going to erase this without taking a picture, okay? All right, so now what we do is we say, okay, my dynamics don't change because that's not something that I can control, but unfortunately, my control variable is going to be m hat times v in this case, where again, v is x model double dot minus 2 lambda x tilde dot minus lambda squared x tilde. okay? And again, if my system was robust enough, I could just throw the control, if I had a good estimate for m hat, I could just throw this controller on there and it wouldn't work perfectly, but it would work okay. I mean, again, if you look at this, this would be x double dot equals m hat over m u, or sorry, v, okay? And so this isn't exactly perfect, the m hat doesn't perfectly cancel, but if m hat over 1 is close enough to 1, everything would be fine, okay? But that's not good enough for me. I want to completely estimate m hat. What I really want is I want m tilde, which I'm going to call m hat minus m. I think that's the notation in the book. Let me make sure. Yeah, m hat minus m. I want this to go to 0, okay? That's what I'd like to happen. So how do I ensure that? Well, first, what I need to do is I need to look at the closed-loop dynamics of the system and put it in a form that I can kind of make sense of it. So I'm going to keep this mx double dot equals m hat v, but I'm going to factor out v for a second. And I'm going to get x model double dot minus 2 lambda x tilde dot minus lambda squared x tilde, okay? And in order to get this to shake out right, what I'm actually going to do is I'm going to subtract mx double dot m minus 2 lambda x double dot x tilde dot lambda squared x tilde. I'm going to subtract that from both sides. On the left-hand side, because I have an m here, I can bring the m in. So I'm going to get x tilde double dot minus x tilde double dot m, which is really just x tilde double dot. So I'm going to get m x tilde double dot. Since I'm subtracting on the right-hand side, on the left-hand side, those minuses are going to carry through, and I'm going to get plus 2 lambda x tilde dot plus lambda squared x tilde. Now, I've already shown this before I erased it, but this is actually my first order system. This is m s plus lambda s. I've already shown that in the previous. So if you don't recall, rewind it. This is that first order transfer function here. Okay. This is going to equal, well, what? This minus this. These are the exact same things. And m hat minus m is just m tilde. So I'm just going to get m tilde v. And these are my closed loop dynamics. Okay, so let's take a look at these closed loop dynamics for a second. If m tilde goes to 0, right, then that means that s dot plus lambda s is 0, has a 0 forcing function, which means as long as lambda is greater than 0, s is going to tend to 0. If s tends to 0, remember that s equals x tilde dot plus lambda x tilde. If s goes to 0, it means that this is going to have a forcing function of 0. So this is going to go to x tilde dot plus lambda x tilde equals 0, which means, again, as long as lambda is greater than 0, x tilde is going to go to 0, which means that x is going to go to xm. Which means if I can get m tilde to go to 0, I can guarantee that I have good tracking performance, which is insane that that all works out mathematically, okay? So how do I make sure that m tilde goes to 0? Well, I need to ensure that my closed loop dynamics are stable, so let's create a Lyapunov function to ensure that my nonlinear system is stable, okay? So my Lyapunov function v is going to be 1/2 something plus 1/2 something. Well, what do I want to go to 0? Well, I definitely want m tilde to go to 0, so I'm going to throw a 1/2 gamma m tilde squared. I know I want that to go to 0. Now, what else do I want to go to 0? Well, I want x to go to xm, so I really want x tilde to go to 0. So if I did 1/2 x tilde squared, I could use that as a Lyapunov function, but the problem is that my state vector, right, is x and x dot, which means I would need 1/2 x tilde squared plus 1/2 x tilde dot squared, and you start taking derivatives and that's going to get really nasty. The better thing is really just use s, right? S is equal to x tilde dot plus lambda x, right? So if s goes to 0, the other two go to 0 as well, right? So then I'm just going to do 1/2 k s squared, okay? Now the k, I could plug in what it is, but I'm going to leave it blank for now. You'll kind of see how it shakes out in a second, okay? So this is positive definite everywhere. S is always s squared is always greater than 0, and m tilde squared is always greater than 0, and when m is 0 and s is 0, my whole system is stable, and that's exactly what I want, okay? So if I take v dot, right, I'm going to get the 1/2 cancels, and I'm going to get ks s dot plus 1 over gamma m tilde dot. Now let's look at m tilde dot for a second. This is m tilde, which means m tilde dot is m hat dot minus m dot. But I'm assuming that m dot is 0. I'm assuming that mass is constant. If my mass is changing, then this is a completely different problem. Okay? The other thing I'm going to look at is this s dot over here. So s dot, right, is x tilde double dot plus lambda x tilde dot. And I don't like that. The reason why is because, again, I told you my state vector is x and x dot. So if I want x double dot, I need to take a derivative. And taking a derivative is typically noisy and all of these other things. So I don't want to do it. So instead what I'm going to do is I'm going to look at my closed loop dynamics here, and I'm going to say, okay, well, I have a ks dot here and I have an ms dot here. I'm going to write ms dot equals m tilde v minus lambda ms, okay? And so what I'm going to do is I'm going to let k equal m, okay? So if I substitute all that in, start sitting down here, running out of room. If I substitute all that in, I get v dot equals, so I'm going to get an s times ks dot. Ks dot is now ms dot, and so I'm going to get an m tilde sv minus lambda ms squared plus 1 over gamma m tilde m hat dot. Okay? So now let's take a look at this for a second. So I have two m tildes over here, so let's factor those together. So I'm going to get v dot is m tilde, and then I'm going to get 1 over gamma m hat dot plus sv minus lambda ms squared. Okay? Now, there's nothing I can do about this. But the good news is that lambda is always greater than 0, m is always greater than 0, and s squared is always greater than 0. Which means lambda ms squared is always greater than 0, which means negative lambda ms squared is always less than 0, which means this term is always less than 0. I don't need to worry about it. Right? Lyapunov stability says as long as v is greater than 0 everywhere, and v dot is negative everywhere, everything's fine. So I really just need to let 1/2 gamma m hat dot plus sv equals 0. Right? So that means that m hat dot equals negative gamma sv. And that's it. There's my update law. If I throw that into my equations of motion, negative gamma, remember gamma is a constant, s is x tilde dot plus lambda x tilde, v is here, this is v, right? As long as I throw this together, xm double dot minus 2 lambda x tilde dot minus lambda squared x tilde, and remember x tilde is, do I have that written down? I don't think I have that written down. X tilde is just x minus xm, right? And then x tilde dot is just x dot minus xm dot. And then x dot and x are here from your equations of motion here. This is a closed loop, so you don't need to simulate that. And then here is your control law u. So you have where are your model reference dynamics? I think that was on a board before. So if you rewind, you have your model reference dynamics to get X model. You have your pseudo control law. You have your actual control law. You have your dynamics that get hit by your control law, and then you have an update rule for your mass dynamics. So you have everything you need to simulate this. And if you simulate this, you'll see that as long as your reference signal varies enough, that is, it changes largely enough, your tracking dynamics will be good after a certain transient, right? Transient dictated by your tracking dynamics here. You'll see that your tracking performance will converge, and your model, your mass estimate will also converge. If you hit this, if you make your reference dynamics just a step, your system m hat won't have enough time to catch up to your actual estimate. So you need to put in a sine wave to sort of excite the dynamics and actually get m hat to fully track your mass, okay? And so that is a practical example of adaptive control, and this feeds in perfectly into what's called parameter estimation. And so that'll be part 3 of this video series, and it's late, so I'll probably post that in a couple days. Okay, I hope you enjoyed this lecture. Have a good night.